I am Shoma Bandyopadhyay, Assistant Professor, Computer Science and Engineering Department of MCKV Institute of Engineering. Today, I will discuss about the decoder and demultiplexer circuit. Discrete quantities of information are represented in digital system with binary codes. A binary code of n bit is capable of representing up to 2 to the power n distinct elements of the coded information. A decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 to the power n unique output lines. If the n-bit decoded information has unused or don't care combinations, the decoder output will have less than 2 to the power n outputs. The decoder presented here are called n to m line decoder, where m is less than the power less than equal to 2 to the power n. So their purpose is to generate the 2 to the power n or less min terms of n input variables. The name decoder is also used in conjunction with some code converters such as BCD to 7-segment decoder. So today I will discuss about the operation of the basic 3 to 8 decoder circuit. The 3 inputs are decoded into 8 outputs, each output representing one of the min terms of the 3 input variables. The 3 inverters provide the complement of the inputs, and each one of the 8 AND gates generate one of the min terms. A particular application of this decoder would be a binary to octal conversion. The input variables may represent a binary number, and the output will then represent the 8 digits in the octal number system. So here for 3 to 8 line decoder that can be used for decoding any 3-bit code to provide 8 outputs. So if we show this table shows the input outputs of 3 to 8 line decoder. X, Y, Z are input, and D0, D1, D2, D3, D4, D5, D6, D7 are the output. So if you observe the truth table, you can find that the output variables are mutually exclusive because only one output can be equal to 1 at any one time. The output line whose value is equal to 1 represent the min term equivalent to the binary number presently available in the input lines. So that means in case of D0, it is basically x complement, y complement, z complement. Similarly, in case of D1, D1 is 1 when x complement, y complement and z. Okay. Similarly, in case of D2, it will be x, y complement, x complement, y, z complement. In case of D0, it is x complement, y complement, z complement. In case of D1, x complement, y complement, z. In case of D2, x complement, y, z complement. In case of D3, x complement, y, z. Similarly, if we see in case of D7, it will be x, y, z. Okay. So this decoder provides the 2 to the power n min terms of n input variables. Since any Boolean function can be expressed in the sum of min term canonical forms, one can use a decoder to generate the min terms and an external OR gate to form the sum. In this way, any combinational circuit with n inputs and m outputs can be implemented with an n2 to the power n line decoder and m OR gates. The procedure for implementing a combinational circuit by means of a decoder and OR gate requires that the Boolean functions for the circuit be expressed in sum of minterms, and this form can be easily be obtained from the truth table or by expanding the functions to their sum of minterms. Suppose we want to implement a full adder circuit with a decoder and two OR gates. So from the truth table of the full adder, we can obtain the function for the combinational circuit. The sum of minterm is x, y, z equal to sum 1, 2, 4, 7 and carry x, y, z sum 3, 5, 6, 7. Since there are 3 inputs and a total of 8 minterms, we need a 3 to 8 line decoder. So for that, for implementation of full adder circuit with the help of decoder, the decoder generates the 8 minterms for x, y, z, and the OR gate for output S forms the sum of minterm 1, 2, 4 and 7. Similarly, the OR gate for output C forms the sum of minterms 3, 5, 6, 7. So a function with a long list of minterms requires an OR gate with a large number of inputs. A function f having a list of k minterms can be expressed in its complemented form if complemented with 2 to the power n to k minterms. So if the number of minterms is a function greater than 2 to the power n by 2, then f complement can be expressed with fewer minterms than required for f. So we can implement the full adder using the decoder and with the help of two OR gates. So what we have to do? We have to first write the truth table, then we write the expression for the sum and carry, and from that we can use the OR gate to make the expression for the summation 1, 2, 4, 7, that is for sum, and for carry it is the summation 3, 5, 6, 7. A decoder with an enable input can function as demultiplexer. A demultiplexer is a circuit that receives information on a single line and transmits this information on one of 2 to the power n possible output lines. The selection of a specific output line is controlled by the bit values of n selection lines. So, the decoder with enable input can work like the work as the demultiplexer. So here we have shown the 2 to 4 line decoder with enable input E, and here we have used NAND gate. That is why if the A, B both are 0, 0, and if the enable is active low, that means if it is 0, so then D0 will be selected and that D0 is active low. That means D0 will be 0, rest will be 1. Okay. Similarly, in case of A0, B1, D1 is selected. So except D1, other bits will be D0, D2, D3 will be 1. Similarly, in case of D3, enable input is 0, A and B both are 1. So D3 is selected and D3 will be 0, all other output will be 1. So here we have used demultiplexer. We have shown that demultiplexer. So because decoder and demultiplexers operations are obtained from the same circuit, a decoder with an enable input is referred to as a demultiplexer. So here the enable input that makes the circuit a demultiplexer, the decoder itself can use AND, NAND or NOR gate. So decoder or demultiplexer can be connected together to form a larger decoder. So suppose we want to make 4 to 16 decoder. We can use 3 to 8 decoder with enable inputs connected to form the 4 to 16 decoder. So here we have used 3 to 8 line decoder. We have used two 3 to 8 line decoder and that have enable input. So with that we will make 4 to 16 line decoder. Okay. So when the here E equal to 0, the top decoder is enabled and the other is disabled. The bottom decoder, the output are all zeros and the top 8 outputs generate the min term from 0, 0, 0, 0 up to 0, 1, 1, 1. When E equal to 1, then the enable conditions are reversed. The bottom decoder's output will generate the min term in 1 0 0 0 to 1 1 1 1. So this when E equal to 1 and this is when E equal to 0. So when equal to 1, the enable conditions are just reversed. The bottom decoder outputs generate the min term 1 0 0 0 to 1 1 1 1, while the outputs of the top decoders are all zeros. So this example demonstrates the usefulness of enable inputs in ICs. In general, the enable lines are a convenient feature for connecting two or more IC packages for the purpose of expanding the digital function into a similar function with more inputs and outputs. Okay. So, today we have learned the decoder circuit. We have learned the 3 to 8 line decoder. Then we have implemented full adder using the decoder. Then we have learned to design 2 to 4 line decoder with enable input, and finally 4 to 6 decoder we can construct with the help of 2, 3 to 8 decoder. Okay. Thank you.